Okay. Um, well, does anyone have any homework questions they want to put out there? Wow, silence. Okay. Okay. Suit yourself. I'll just start covering stuff then, and we'll see if we have any uh, time at the end. Um, okay. Okay. So last time we saw how to compute the QR factorization of a m by n matrix of full column rank with Gibbons rotations. And that certainly is one very effective tool. But so today we're going to look at another one that will be useful not just for the QR factorization, but for other problems, as we'll see um, later on in the semester. Um, okay. um, these are called household reflections. Okay. Okay. All right. So now, the strength of Gibbons rotations is that if because of a pinpoint action, like they're used to each Gibbons rotation will be used to zero just one element of a matrix. So in cases where you need to be more particular about what you zero, like maybe A is a sparse matrix, so you want to only zero a few select elements. Gibbons rotations are great for that because they'll get that job done efficiently without any wasted computation. But it turns out that Gibbons rotation, while maybe the most versatile approach to the QR factorization, is actually not the most efficient. Um, so that's where householder comes in. Um, so household reflections, you could say that they're a lot more destructive than uh, um, they're a lot more destructive than Gibbons rotations because whereas Gibbons rotations will only zero one element at a time, household reflections can wipe out most of a column all in one shot. So use of caution. Um, so a householder reflection, and I'll explain in time why it's called a reflection. It's also known as a householder transformation. Um, it's going to have this form: identity minus some constant times UU transpose. Now, U is a non-zero column vector. So we've seen this before where UU transpose um, is an outer product. So I'll just mention that here. Stop it. I hate when this thing puts in backslashes where I don't want them. Um, so UU transpose is an outer product which is a matrix. So an inner product of two vectors is a number. Outer product of two vectors is a matrix. So we like to choose the constant tau so that this matrix is orthogonal because we want to use orthogonal transformations because we're trying to compute the QR factorization where Q is orthogonal. So we want P transpose P to be identity so that P will be orthogonal. So what I do is I actually fill in this form for P and go ahead and compute P transpose P. So here we're foiling, and UU transpose is a symmetric matrix. If I take the transpose of UU transpose, remember, transpose of a product is a product of a transposes in reverse order. So it'll just be UU transpose all over again. And we actually have these two terms that'll combine to give -2 tau UU transpose. And then and then we have this from these terms multiplied together. Now, what's interesting is here I have UU transpose, and U transpose U in the middle of all this, that is an inner product, and that's just a number. So I'm allowed to take this U transpose U and move it around wherever I want. And then I still have this U and U transpose left over. So that's one of the interesting things that happen when you multiply an outer product with a vector, then you get an inner product. And that's useful for a lot of things. Okay, so then notice that both of these terms have UU transpose in them times different constants. So these are like terms that can be combined. So, and a tau is a common factor. I'll pull that out. So then I just have this factor right here. So I want P transpose P to be identity. So I want all of this to be 0. Well, tau is non-zero. U is non-zero, so UU transpose will be non-zero. Therefore, the only possibility is that this is 0. So I've solved for the constant tau. And so if I choose tau to be this constant, 2 over U transpose U, then P is an orthogonal matrix. Now, U is non-zero, so I could just say, well, I can require that it's a unit vector. I can normalize it. So now I can write P this way. Basically, I'm replacing, I can define V to be U divided by its 2 norm. So it's a unit vector. So any householder reflection has this form, identity minus 2 VV transpose, where V is a unit vector. So V transpose V is 1. Okay. Now, okay. Actually, one thing I want to make sure that I also mentioned, and I'm kind of surprised that in my notes it hasn't popped up already. Okay. Well, I'm kind of cheating here. Okay. Oh my God. And I'm looking through like what I have the oh, okay. There's something at a very important property of P that is mentioned here, but maybe not mentioned clearly enough. So I want to emphasize it here, and I'm honestly, I'm surprised I didn't in the book. Okay. Now P is orthogonal, but what I mentioned up here, just by making P of this form to begin with, this is symmetric. Identity is symmetric. Therefore, the whole thing is symmetric. So we have a matrix that has a unusual property P is symmetric and orthogonal. Whereas a given rotation, that's just plain orthogonal. It's not symmetric. Now, what does this mean? So this will be pretty convenient for us. Because P is symmetric, P is equal to its own transpose. Because P is orthogonal, P transpose is equal to P inverse. That comes from P transpose P being identity. What can we conclude from the two of these together?
P equals P inverse.
Yes, P is its own inverse. So P squared is equal to identity. Okay, so because you would think that the only kind of matrix that would have that property is like either identity itself or like minus identity or certain other tweaks thereof. But here's a matrix that every element can be non-zero. So far from a diagonal matrix, but it's still you square it and you get the identity matrix. Okay. Now, I want to talk about the geometric interpretation of P, why we end up calling it a reflection. Because if I multiply P by a vector, it ends up reflecting X across a hyperplane that's normal to V. Now, what do I mean by that? I'll show you like in a more equation-y fashion. Okay, so I'll do a 2x2 example. V is just a vector for the x-axis, so pointing in x direction, and then I just make up some random vector x. So then I define P, and I'll fill in what V is here. So what I work out, identity minus 2 VV transpose for this V, this is what I get. It's a matrix that if you multiply it by a vector, it's going to negate the first element and leave the second element alone. So if I compute P times X, I multiply it by the vector 1, 2, and I get minus 1, 2. So it is reflected the vector X across the y-axis, which is orthogonal to V. So you see that's a reflection in that case. Now, suppose I choose a different vector, 2 minus 1. Well, okay. Wait, something's wrong here. Okay. Wait a minute. Do I have something here that's totally wrong? That's going to really piss me off. Anytime I find a mistake in my notes, and it's like, well, that's a mistake in the book too. So, okay. I'm going to have to change the example. Let's say if y is equal to, yeah, this vector, y is orthogonal to x, but I need a vector that's orthogonal to v. So if I compute py, okay. So I'll write this in more detail. So that's identity minus 2 VV transpose Y but that's the same as y minus 2v v transpose y. But v transpose y is 0. So I just get y here. So, okay. Okay. So what ends up happening is if I have any direction that's orthogonal to v, then p is going to leave it alone. It's going to preserve those. But if there is a component in the direction of v, then that component is going to be is going to end up being negated. All right. So to summarize what's happening geometrically, okay. So if v transpose, so this is in general, if v transpose x is equal to 0, then p x is just going to be equal to x. On the other hand, if I compute p times v, well, that's identity minus 2v v transpose times v. So that's going to be v minus 2v v transpose v. Now, v transpose v is an inner product. I'll put parentheses around that. But v is assumed to be a unit vector. I want to emphasize that here. So because a 2 norm of v, which is a square root of v transpose v, is equal to 1, then that is 1, and I get just v minus 2v and it's just minus v. So this householder reflection preserves vectors in n minus 1 dimensional subspace that's orthogonal to v, but p times v itself negates. So that's why it's a reflection. It's negating one direction, preserving all the directions that are orthogonal to it. So that's causing reflection across a certain plane. Okay. Now, we want to use this. Well, first, any questions about what's happened here? I realize that things haven't gone smoothly because of one mistake I discovered. Dang it. Okay. We want to see how this can be used to zero out elements of a column of A to try to reduce it to upper triangular form. So before I move to working on a matrix A, I'm just going to work on a vector X. I want to be able to zero out elements of X. So my goal here as a precursor to QR factorization is if I have a given vector X, I want to find the householder reflection P of this form where V is a unit vector So that if I multiply p with x, I get a multiple of E1. This is E1. It's a vector of 1 in the first position. All others are 0. So the reason why I want to do that is that means that by multiplying x by p, I zero out all of the elements of x except the first one. Okay. So the question is, what is the magic vector v that will make this happen? Now, one thing to keep in mind is P is an orthogonal matrix. So if I multiply P by X, the 2 norm is not going to change. Now, Px is alpha E1. So if I compute the norm of this, well, the alpha is a scaling factor. It gets pulled out. So I have a norm of E1. But the norm of this vector is just 1. Because remember, it's the square root of sum of squares. So I just get alpha. So what that means is alpha has to be equal to plus or minus the 2 norm of x. All right, so at least I have some idea of what that constant is going to be. And I don't really care which at the moment. So either one will do. So how do I get v that will make this happen? Well, I start computing p times x. So I fill in what that is. So I distribute. So I have x minus 2 vv transpose x. And that is equal to this alpha E1. So I want to make sure that this happens. So now, if I rearrange that, then, so I move the alpha E1 over here, divide by 2, and then I have this V transpose X times V, because remember, V transpose X is a inner product. So what is this equation telling us? It's saying that, okay. All right. It's saying that this vector must be the direction of v. So, because what is this? This is just a constant scaling factor times v. So the direction of v must be the same as this direction. So we know the direction of v now. We also know the magnitude of v, because v is assumed from the beginning to be a unit vector. So in other words, we can take a vector x minus alpha E1, where we know what alpha is, at least up to plus or minus, and then normalize it. And that would be a v that would work. Okay. And of course, since I'm talking about both the magnitude and direction of a vector, I can't help but recall the first Despicable Me movie, where the villain is vector because his crimes have both magnitude and direction. But sorry. If I weren't teaching, I'd see myself out now. So now what I'm going to do is I'm going to look at the vector v that we have here, component by component. So the first component would be first component of x minus first component of alpha E1. But E1 starts with a 1, so it would just be alpha. And then I'm taking this vector and I'm normalizing it to make sure that it's a unit vector. Now, I can try to write out what that is, because I'm taking a square root of sum of squares of this. Well, I would be taking the well, the norm of a difference of vectors is the norm of a first one squared of the norm of a first one squared minus 2 times the dot product of these. But all the elements of this vector are 0 except the first one. So I'd have alpha times 1 times the first element of x, which is x1, plus the norm of this squared, which is alpha squared. So now I have this relationship here.
Dr. Lambers,
Yes.
I know you sort of explained through that. Maybe I missed something. I still don't understand how you can just pull the rest of it out of the norm from the first line to the second. Like
From here to here.
yeah, how you put the norm of the x squared, and
Oh,
then the rest of it just came out of the.
okay. I'll add a intermediate step. Oops. Okay. Whoops, something went wrong here. Okay, I wanted to copy. Dang it. Sorry, this thing is being a bit uncooperative. Okay. All right, so if I express the denominator here as, okay, square root of the 2 norms squared. So we have this relationship with that describes a 2 norms squared of a difference, but although that's the same as the 2 norms squared is also the inner product of a vector with itself. Okay. So now I'm basically foiling this. And what will I get? I'll get x transpose x. That's a 2 norm of x squared. And then I have alpha E1 transpose x, but E1 transpose x, that's just the first element of x. And then same thing from the outside terms. And then I take alpha squared E1 transpose E1, but that's just going to be 1.
Okay, that makes sense. Thank you.
Okay. All right. So now, okay. Now, what I'm doing here to get from here to here is, remember, alpha is plus or minus the 2 norm of x. So this 2 norm squared of x, that's just alpha squared. So these two alphas add together, and that gives me this.
I think you forgot a square
Um,
when you add them, right?
oh, I get 2 alpha squared minus 2 alpha x1. I factor out a 2 alpha.
Oh, okay, I gotcha.
Okay. All right. Now, a way that I can simplify this, notice I have alpha minus x1 up top, and then alpha minus x1 below inside the square root. So what I can do is I could think of this alpha x1, alpha minus x1 up top, as equal to, so like if I were to rewrite this as square root of alpha minus x1 squared, I can do that except for one problem. That's not alpha minus x1. That's the absolute value of alpha minus x1. I also would have to introduce this, the sign of alpha minus x1. Okay. Okay. But something to keep in mind here is alpha is plus or minus the norm of x, the whole vector x. So if I choose the plus sign, that's going to be greater than x1. So that'd be positive. If I choose a minus sign for alpha minus the norm of x, this whole thing will definitely be negative because, again, it's larger magnitude than x1, because x1 is just a component of x. Stop that. Okay. So sine of alpha minus x1 happens to match sine of alpha because alpha is guaranteed to be greater in magnitude than x1. So now I can simplify here and I get this. So here's my simplest possible expression for first element of V using what we know about alpha. Then other elements of V will actually be simpler because V is defined to be this, but for and then we take its vector, we normalize it. Well, this is only subtracted off for the first element. So for the second element on, the numerator is just going to be element of x2, and then the denominator is the same. It's this, which I'd previously simplified to this. So that's what we get for the second element, and then okay. But using the expression we already have for V1, we can simplify we can simplify a little bit further because notice in our final expression for V1, we have square root of 2 alpha in the denominator in both cases. So then I can simplify. I can use this formula in combination of this one to get this. So once I computed V1, this is actually simpler. Why? I don't need to compute another square root. The only square root I need to compute is this one. And I think a square root is several floating point operations, all in one shot. And if we can avoid that, it'd be preferable. And then all other elements of V are just like V2. So the pattern just continues like that. So that is our most efficient way of computing V. That we just compute this first element, V1 here, and then that is used to compute all the other elements very quickly. So basically, we're taking a rest of a vector x minus that divided by 2 alpha V1. Okay. Now, I still haven't specified, like, if we're going to choose alpha to be plus or minus a 2 norm of x, is there a preference? Is there a good reason to choose one sign versus the other? And the answer is yes. If we look back here, here we have alpha minus x1. So suppose what we should do is choose the sign of alpha so that this is an addition rather than a subtraction. So like if x1 is positive, choose alpha to be minus the 2 norm of x, because that way we have 2 negative numbers being added. Similarly, if x1 is negative, so this becomes a plus, then we choose a plus sign for alpha. So either way, you're choosing sign of alpha, so it's the opposite sign of x1. So that's a safer floating point operation, because subtraction can be risky if you have cancellation of digits. So what we can do is compute V very efficiently. So after we compute V1, which requires a a subtraction, a multiplication, a division, and then a square root. So 4 floating point operations there. Then what we can do for the rest of the vectors, we go ahead and compute 2 alpha v1. And then we divide all the rest of the elements of x. So that's only 1 floating point operation per component for everyone except the first. That's why I say it's about n. It's slightly more than n, but only a little bit more. And that's why I went through all this trouble to do these simplifications to cut down a number of operations, especially square roots. Okay. Now, cardinal rule of working with householder reflections: never, ever, 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 ever form the matrix P explicitly. That is a waste. If you want to compute P times a vector B, this is what you do. You just you compute this term, just subtract it off from B. So, because a matrix vector multiplication generally is order n squared operations. But this process here requires only about 4n operations, because the inner product will take roughly 2n. Then you multiply that by each element of V, so that's 3n. Then subtract from actually the 2 can be folded in to that, and then subtract off from B. So 2n, n here, 4n total. So much more efficient than a full-blown matrix vector multiplication. It cuts off an order of magnitude work. Also, you don't need to store P, because once you know V, you know what P is. So implicitly, you represent P by storing just V. So you're saving order of magnitude for storage and computation. Okay. So now, finally, we want to talk about QR factorization. Because suppose the vector x that we're trying to zero out entries of is the first column of the matrix A. So now you can construct a householder reflection using a procedure I described earlier, so that H applied to this first column of A zeroes out everything except the first element. So now, kind of like with Gaussian elimination, we've just finished working on the first column of A. So what happens? You have this new matrix here. So this is what we get from working on the first column of A. Everything's 0 except the first element. And then everything here is changed by multiplying by H1. But now we need to wipe out the subdiagonal entries of this part to eventually reduce A to upper triangular form. And R11 is the constant alpha, because this will eventually be our matrix R from the QR factorization. So now we move on to the second column. So we take this portion of the second column from the diagonal on down. So every element except this one, the first one. We find a household reflection that will wipe out all this. So now, how does this affect the overall matrix A when we do this? Well, the thing is, this first householder matrix affected the entire matrix. H2 tilde here does not. It only affects this lower n-1 by n-1 part. So if I define this matrix to be have a 1 here, and then the household reflection here, I needed this to be, sorry, not n, m by m, then I have this matrix that's made more progress towards upper triangular form. And then I can continue this process. Okay. So how would this keep going? Now, the thing to keep in mind is at least because of this 1 here, and the fact that H2 is only going to affect rows 2 to the bottom. It will not touch anything that happened here, because yes, H2 tilde is being multiplied with all this, but all of these are 0, so they remain 0. Okay. And that's what the point I was just making here. So in general, we multiply A by household reflection to work on columns 1, 2, 3, up to n to get this upper triangular matrix R. And a way to find each one of these household reflections is I have an identity matrix of size j minus 1, and then this is a household reflection that actually works on zeroing the portion of whatever column you're in. In this case, it's column j. So with H1, I have nothing here. I just have a household reflection. With j equal 2, I have identity that's a 1 by 1, and so I have a 1 here, and then H2 tilde. So if I move to j equal 3, I'd have a 2 by 2 identity here, and a smaller household reflection here. And that is what will reduce A to upper triangular form. So questions about the process? I have an example anyway. Okay. Similar to the Gibbons example from last time. I have a made-up matrix here. Actually, it might be the same matrix. I don't remember. And so what I want to do is reduce this to upper triangular form using 3 household reflections. So what I do is I take the whole first column. That would be, I'll call this X1. I find its 2 norm. Whoops. So V is going to be X plus the norm of X1, because what happens is, because X1 is positive, I want to choose a minus sign for alpha. So alpha is actually equal to minus the 2 norm of X1. So now I form my vector V for my household reflection. And something went wrong here. I think I might have accidentally deleted something. Oh, I see what happened. There it is. Okay. So I have my 2 norm times E1. So that is my vector V for my household reflection. So now, if I define this constant, because this is not a unit vector, I need V to be a unit vector. So I'm basically going to normalize it here. And now I make my household reflection. And then when I apply this household reflection to A, and this is what I get. And here we have alpha, which is minus the 2 norm of a first column of A. And then the rest of the first column is zeroed, and these upper columns are at least modified. Okay. So this is my updated matrix, which I'll call A2. So now I work on the second column. So I just need a portion from entry 2 to the bottom. So I don't take the last 4 entries, take a 2 norm. And then here, the first element of this portion of the second column is negative. So my vector v will have a minus this time. So I'm subtracting, so the norm of x2 times e1, and that is my vector v for my household reflection. That's going to work on column 2 and rows 2 through 5. So I make my household reflection, and I apply it. And working on columns 2 through 3, that's what I get. But now I want to apply this to the entire matrix A. So this part gets stuck back in here. Okay. So now I have one more column to work on. So just this portion of the third column, take its 2 norm. And all right, so I for my V once again. So then I make my household reflection, and I apply that, and working on just the third column, wipe out everything except the first element of that. But then I put this back in the overall matrix, and now it's upper triangular. So now I'm done. So to summarize what happened, my matrix Q is this product of the 3 household reflections, H1, H2, H3, that reduced A to upper triangular form. And the thing is, each household reflection is its own transpose and its own inverse. So H1, H2, H3 is Q. H3, H2, H1, so in reverse order compared to here, that's Q transpose. Now, to fully show you what H1, H2, and H3 are, H1 is just the entire household reflection I used the first time. H2 is the household reflection to work on rows 2 to the bottom with a 1 here. H3 is a household reflection that worked on the third column with a 2 by 2 identity matrix. That way, every single one of these matrices is M by M, 5 by 5. Because H1 tilde is 5 by 5. This is 4 by 4. This is 3 by 3, because each household reflection in turn is zeroing fewer elements. So each of these H tildes are smaller. Now we could think of each of these, H1, H2, H3, as a household reflection of this form, where the vector V in question has leading zeros, because these V tildes are the ones that actually use to zero out portions of columns. But each one is working on a shorter and shorter column. So the actual household reflections that are reducing A to upper triangular form are working with V's with fewer and fewer non-zero elements, because they're working on a smaller and smaller portion of a matrix. So, any questions about what happened in this example? Or have I fried all your brains? In which case, I feel especially bad for those of you who are about to sit through PDE. All right.
I don't really understand what happened. Just an observation. Because I realized we were working with the same matrix, but our R was different. Is that usually the case when we use auxiliary reflections and when we use givens?
Oh, actually, that's the very next thing for me to talk about.
Okay.
Yeah. So the QR factorizations are similar, in that okay, the first three columns of Q match up, except it might be negated. So yeah, so there may be a sign difference, because what you can do is look at the matrix R. In this case, we have two elements that are negative, whereas givens rotations, the way we've defined them, use a convention that you're zeroing a certain element, and then the other element is set to be positive. So that has the effect of making all the diagonal entries of R positive when it's givens, but that's not necessarily the case of Householder. The reason for that is that Householder has this criteria of needing to choose signs a certain way to have better floating point arithmetic properties, and givens does not have that issue. So that's why they might not it might not necessarily be equal, although certainly kind of resemble each other. All right.
For the givens, when we did the givens, the last diagonal entry was actually negative.
Oh. Okay, that's.
I don't know if that's an error in the textbook.
Part of me hopes it is. Let me. Yeah, that's kind of strange. Okay. If I go through that, all the givens rotations that happened. Okay. Oh, yeah, I see what you mean here. Yeah, that's. Oh. Yes, it is an error. Dang. Because right above it is where the givens rotation is applied to those two elements and makes that what's supposed to be last diagonal entry positive. So yes, that does need to be fixed. Okay. All right. So that's on page 136. Okay. All right. Now, also keep in mind that the 5x5 matrix Q that's produced by givens or Householder, the fourth and fifth columns don't match. Not even like negation, but they do span the same subspace of dimension 2. That's not that one is orthogonal to the columns of A. So because for a given subspace, you can have infinitely many orthogonal bases. So it just depends on the algorithm which one you're going to get. So you can never expect the columns past column n will not necessarily match. But since they do span the same subspace, there's a definition that I want to give here. And this comes up in a linear algebra class, but orthogonal complement. So you have a subspace of a vector space. All the vectors that are orthogonal to every vector in S is called S perp. So that is the orthogonal complement. So every vector in S perp is orthogonal to every vector in S. So basically, you're dividing a vector space V into S and S perp. So the first n columns of Q span a column space of A. The other columns of Q span the orthogonal complement of a column space of A. Okay. Okay. Oh, and that's actually what I was just mentioning here. So 5x3 matrix, first 3 columns span the range of A. That's all linear combinations of the columns of A. 4th and 5th columns span the orthogonal complement of the range of A. Okay. Okay. All right. Now, whoops. Okay. All right. All right, so then I'm going to show you the actual algorithm. So I have these equation references. They'll be fixed when I post the notes. So I'll show, like in a quasi-MATLAB style, what the algorithm for householder QR looks like. Okay. Okay. So our matrix A coming in, we set Q initially to be identity, like in the givens algorithm. R will be equal to A. So then we're just going to work with R from this point on. Okay. Oh, I see I have a missing parenthesis here. All right. So what I do is I have a helper function house. Now, what does house do? House is a function that computes the vector V using the formulas for the elements of V that I gave earlier. Although not necessarily assuming that V is a unit vector, that's not required here. But for a given householder reflection, the function house will compute the vector V. So that's what we do. We look at column J from a diagonal to the bottom. It's kind of like Gaussian elimination in that sense, because we're trying to make it upper triangular. Same goal. So now we define a vector V that will zero out all of this except the first element. So then I compute this constant for convenience, 2 over V transpose V. And then this line will multiply R on the left by the householder reflection. And that'll have the effect of zeroing out the portion we want zeroed out in column J. Notice we only look at rows J to the bottom and columns J to the end. Why? Because V is only needing to work on that portion of column J. So it's almost like implicitly, if we had an M by M householder reflection, the first J minus 1 elements of V would be 0. So we don't need to touch the top rows, only rows J to the bottom. Also, columns J to N, we don't need to touch the columns to the left of column J. Why? Because that portion of the previous columns is already entirely 0. We would just be multiplying by zeros. Okay. So this multiplies householder reflection on the left. Then we take our Q and multiply by the same householder reflection, but on the right. Notice we have V transpose R. Here I have Q, V transpose. Q is on the opposite side of a V transpose. So by accumulating to the right, we get our matrix Q for the QR factorization. Now, we don't absolutely have to compute Q explicitly. We could just store the vectors V and that would give us enough information to reconstruct Q if we needed it, or to multiply matrix by Q or Q transpose if we needed to. Now, here we are messing with columns of Q because we're multiplying on the right. That's why we only touch columns J through M, for the same reason that we only touch rows J through M when multiplying on the left. It's because of the limited impact of V, that V is only working on this portion of column J. But notice the difference here. With Q, I have to apply to all rows, even though I did not have to apply to all columns in R. Why? Because R is being reduced to upper triangular form. As I mentioned, a portion of R is already 0. That's not happening with Q. That's why we have to deal with all rows in this case. So it's important to try to figure out when you're multiplying by a matrix, what portion is going to be affected, and then only work on those rows and columns. That saves floating point operations. Any floating point operation that can be saved, we need to try to save, because these are methods for large-scale problems. And this is what a comment I made here, that we don't have to store Q because we can just store for these. And if M is much larger than N, so if A is a tall, thin matrix, that can really save a lot of storage space. Okay. Okay. So, questions about this algorithm? I'm looking at the problems that I assigned for this homework. 1, 2, 3, 10. Oh, actually, I don't think wait. Oh, I don't have the problems in this file. I assigned problems 1, 2, 3, and 10 from this section. I have one more algorithm for QR factorization, which is Graham-Schmidt, that I'll cover on Monday. One of the homework problems is to implement that one, and the algorithm for that is given in the book. It looks like I actually do not have you implement this algorithm. Okay, so I have you implement Givens QR and Graham-Schmidt, but not this one. Okay. Well, I figure the problems I've given you lately with Gaussian elimination and pivoting have been suffering enough. Okay. So, all right. Are there questions of any kind? Y'all are making this too easy on me. Which I know this bunch. I know I'll have questions later. Okay. Well, I guess I have extra time to prepare for PDE, and I actually need it. So the less fortunate among you, I will see you in 20 minutes. Okay. And I'll stop recording at this point.